Hello and welcome to the lesson on conservation of momentum in one dimension. Our goal today, I want you to be able to explain the meaning of conservation of momentum, and you can apply it in one dimension. So what does the law of conservation of momentum state? It states that, very similar to the law of conservation of energy, that the total momentum in a system before a collision is equal to the total momentum in the system after the collision. So, in easier terms, the momentum, with a vector symbol on top, momentum in the system is equal to P prime, which represents in physics the after part of the system. So now we're dealing with multiple factors. So what does that exactly mean? Well, momentum of the system equals momentum in the system after a collision. So what was involved in the first, before the collision? Well, you'd have mass of object 1, velocity of object 1, plus mass of object 2, velocity of object 2, plus however many objects were involved prior, it will equal the mass and now the new velocity, so v1 prime. So that new mass, the momentum is changed in some fashion. However, if we add up or sum all our masses, all our momentums, they will be in fact equal. Oops, that should be v2 prime to represent the after situation. So what are we really doing here? Because mass is constant, we're essentially analyzing, I'll put an S in this time, analyzing the change in velocity of each object. And again, that's because the mass of each object, we're assuming that they don't break apart or explode on impact, the mass of the object remains constant. So an example, 75 kilogram man standing on a stationary raft, so they're out in the middle of the pond, and the mass of the raft is 55 kilograms. He walks toward the front of the raft with a velocity of 2.3 meters per second, south or west. What's the resulting velocity of a raft? So if everyone's been on a raft or canoe or something, hey, if the person walks that way, the raft underneath you is actually going to slip out, and that's why people fall in the water when they stand up in canoes. So please don't stand up in canoes. Try to walk around. Anyhow, what's happening here? Well, basically we just got to analyze what's the momentum in this system prior, momentum in the system prior to the man moving, setting it equal to, because momentum is always conserved, the momentum in the system afterwards. So what do we got? Well, mass of man, velocity of man, plus mass of raft, velocity of raft, equals mass of man won't change, velocity of man does change, plus mass of raft, and same thing, velocity of raft after the interaction. So if the man starts out standing on the raft, this 75 kilogram man is not moving if he's standing on the raft, so his velocity is 0. Plus the raft is also not moving under the man. However, when that 75 kilogram man moves and he walks toward the front of the raft with 2.3 meters per second, then that mass of raft is going to move. So 55 multiplied by v raft prime. The left side of this equation all goes to 0. So I'm going to bring, doesn't matter which value over, negative 75 times 2.3 equals 55 velocity of raft. Divide both sides by your 55, isolating for the final velocity of the raft. And we find out when you do your calculation that the velocity of the raft is 3.1 meters, and it's negative meters per second. And what did I assume in there? 2.3. I said west was positive, which is kind of counterintuitive. So that makes sense. If the man moves to the west, then the raft will move to the east. So therefore, the raft will move 3.1 meters per second east. So it's not the same velocity because the masses were different, but that is the resulting velocity of that raft, and that's what happens when you're moving on floaty devices in the middle of water. You fall off. During a football game, so fullback, mass of 108 kilograms, runs with that velocity east, gets tackled by a linebacker, 91 kilograms, so a little bit smaller, coming right directly at him, so it's a head-on collision at 6.3. What is the velocity of both men during the tackle? So there's a bit of an assumption here for the non-sports people. Assume both bodies stay together during tackle. All right. So as that tackle occurs, both men remained wrapped up together in one massive, sore-looking ball of contact. So I'm going to assume east is positive. So what am I looking at? Well, I'm looking at two individuals. So I'm going to look at the mass of person 1 plus V1, or sorry, times V1, multiplied by the mass of the second player and their velocity. And it's going to equal, and in this case, because after the collision occurs, they are staying together. So it means that they are going to have a total mass. They're going to get combined together. And since they are combined together, they're going to have a final velocity or total velocity at the end. So that's why it's a VT. Doing my substitution now, we know that the 108 kilogram player was heading east at 9.1, plus we know that the 91 kilogram player was heading 6.3 west, so it's a negative 6.3. My mass total is the 108 plus 91 VT. All right. So what we can do then, we can go ahead and simplify. So you have 108 multiplied by the 9.1 plus the 91 minus 6.3. That's going to be divided by 108 plus 91. That'll give us the final combined velocity of these two gentlemen that are wrapped up in a painful looking collision. And when you run that through your calculator, you end up with a positive number, 2.1 meters per second. And since I assumed east was positive, that's going to be the resulting direction. So that means that the fullback is going to win. The person who is running east, the larger player with the ball, is actually going to run that other player over. So that player that was heading west at 6.3 meters per second, they are going to have an abrupt change in direction, which causes concussion and pain. So therefore, the two players will roll at 2.1 meters per second east. At least that's initial until they end up ending their roll. All right, so there we go. So when we're looking at one-dimensional, we're only looking at head-on collisions here. We're not going to be able to move out of the plane. You are moving simply left and right, and that's your only options. We're going to look at two-dimensional next step. Last example, a 0.0045 kilogram golf ball. So this is the golf players in the room. Is hit with a driver. The head of the driver has that mass, 0.15 kilograms, and travels at a velocity 56 meters per second before the collision, and a velocity of 47 meters per second after the collision. So there has been an energy transfer to the before and after. So we have mass of ball, velocity of ball, and that's before the collision, plus mass of club, velocity of club, and it's got to equal, the momentum has to be maintained here, so we got to have that mass of ball remains the same. The velocity of ball is going to change though. Similarly, we know that the mass of the club stays the same, but we also know the velocity of that club has changed. So starting it off, mass of the ball is given, 0.0045 kilograms. What's the velocity of the ball? So for people that don't play golf, it's sitting on the tee, so it's not being pitched or thrown at the player, although that would make golf a little bit cooler maybe, who knows. So it's 0. we know that the mass of the club, 0.15, and this is why those clubs, there's rules on limitations on the size and weight of those clubs. So for the people who try to load their clubs, this is where the advantage comes in. And it's traveling at 56. Excuse me. And mass of ball hasn't changed, but now it's got the mass of the ball now has now we'll have a velocity. It's been struck, it's moving, and the person that's swinging the club has passed through, made the swing, and the velocity of the club has changed. Now the reason it's changed is because some of that kinetic energy from swinging the club has been transferred to the ball. So we can determine the velocity of the ball in that transfer through momentum. So this is where the energy, kinetic energy unit in grade 11, this is your connection to momentum. So there's been an energy transfer, so we can use momentum to determine that final velocity. First term is going to go to 0. Isolating for VB, I'm going to have 0.15 times 56 minus 0.15 times 47. And that's all going to be divided by 0.0045. You can solve that however you want, whatever you're more comfortable with. I'm just showing it without the calculation so you can know when you look back what exactly the steps were or what was involved. So now I find that velocity of the ball after the collision is 300 meters per second. 300 meters per second. And I'm going to say forward. All right, so there we go. So that golf ball is launched at a very, very high velocity at impact, and then air resistance and other factors slow it up. So therefore, the launch velocity of the ball is 300 meters per second, and that is forward. And there you go. So there is your momentum in one dimension. So like I said, everything's left and right, so it's kind of nice. We're not into the vectors yet. And there's the assigned homework questions. If you have any problems with that, please make sure you come talk to me or ask me, and I will definitely wheel around and give you a hand clarifying that. Good luck, and we'll see you tomorrow.